don't forget, we'll have an extra class on Friday, same time. So. Okay, so last time we were looking at the concept of convolution filters. And we discussed that a few properties of convolution. Convolution is a fundamental mechanism in nature. So all linear systems, the way they behave is, if we feed in an input, the output is always a convolution of the input with the what we call the impulse response of the system. So, so any linear system we have. So x of t okay, so x of t is the input. Then as we discuss, y of t is convolution of x of t. We'll represent convolution with an x with a circle in it. So is h of t. So this is what we call the impulse response, meaning the output that we get if the input is delta of t. So if we feed to the system an impulse, then this output is called h of t, right? So for every linear system, the output is a convolution of whatever input we give with the impulse response. And a few other small things that you need to remember is, if we take a look at the actual integral, this was something x tau, sorry, x tau. T minus tau, meaning we flip this, start sliding, multiplying and integrating, right? Okay, we can do either way. Either we flip this and slide and integrate, or flip the h of t, so it doesn't matter. Okay, so we also discussed that time domain is equivalent to for our images, I mean, is pixel domain. So whatever operation we do on the pixels is equivalent to what we do in time domain on the signals, right? Okay, another important concept was multiplication in time domain is equal to convolution in frequency domain, and vice versa. So multiplication in frequency domain will become convolution in time domain. So this concept is important for us because as we design filters, we come up with certain kind of goal. For example, we wanted to remove high frequencies from an image, or we wanted to pass a certain band of frequencies and block the other frequencies, right? So intuitively, as I discussed, let's say you are given some kind of cloud background with some, also bluish color. So from a frequency component point of view, high frequencies are generated when there's a sudden change. Okay, so this will have very low frequency content, if the background and the image and the foreground, meaning whatever objects we have, are similar to the background, right? On the other hand, let's say you created a picture, there's a table over here with a certain color, blue or red, or doesn't matter. Okay, and the background is, let's say, light yellow or whatever the color on the walls is. Then anytime as we go from here to here, there's a sudden change in color. The sudden change in color produces high frequencies. Okay, so once we do the blurring, okay, then what happens is basically the edges sort of like diffuse with the background gradually. Okay, so this is basically removing high frequencies from the image. So anyway, gradually you'll get better understanding of it. But anyway, so like I was saying, typically our goal is that our whatever filter we wanted to design will be given some kind of a goal in the frequency domain. For example, we wanted to create a low pass filter, right? So in the frequency domain, so the goal might be, okay, pass a certain frequencies. So this is frequency over here. Let's call this H of F. So this is the impulse response in the frequency domain. Suppose it passes all the frequencies, then after a certain frequency, it blocks those frequencies, right? Okay, so how do we create this low pass filter? So if we created let's say we feed in an image. Okay, so this is our filter. So image filter now. Okay, so as we discussed, because the filter is like a linear system, right? So the output over here will be a convolution of input. Okay, so remember input, image in pixel domain. So pixels. So just like I said, in time domain, the output is a convolution of the input with the impulse response. Very similarly over here, the output will be a convolution of the input in the pixel domain. So in pixel domain with whatever is the impulse response of this particular filter. Okay, so this impulse response we refer to as a kernel. So in image processing, vision, rather than calling it as an impulse response, we call it the kernel of the filter. Okay. So what we were trying to do in the last lecture is get a good understanding of, given a certain goal, how do we come up with the kernel, right? So because the concept is important, I'm refreshing some of the important concepts with you guys. So the first concept was if there are some changes occurring in a signal, and so these changes are basically high frequencies. Okay, if we wanted to remove the high frequencies, we pass it through a low pass filter, right? And the easy technique for creating low pass filter was simple averaging. Okay. So in case of stock market data, I give you an example. If we average the price over the last 5 days or 7 days, and then we plot that average, it will tend to smoothen it out. Okay. For filters, how do we get what kind of kernel do we create if we are given some kind of pixel data, right? So if this is the image, we'll do a convolution with a kernel. Okay, so if we wanted a low pass kernel, easy way to accomplish the averaging was pick a kernel, which is 1, 1, 1, 1, 1, 1, 1, 1 divided by 9. Okay, so remember the way it works is we put this 3 by 3 kernel over here, multiply, add with the original pixels. So divide by 9 basically is taking an average of the 9 pixels. Then we move it 1 pixel to the right, we move this window 1 pixel to the right, keep going in the first row, then we start moving this window, 3 by 3 window down So we keep doing an average of 9 pixels, and it will end up removing the high frequencies from the image. Okay? So think of it this way. Let's say in the image there was some kind of a table. So once again, there's a table with certain color, right? And the background color is different. So if we are taking the average of the pixels, so let's say this is a dark pixel, right? Or let's think of it in grayscale for the time being. So if it's a dark pixel, the value will be high or low on the 0 to 255 scale. Low. So it might be pixel value 25 as an example, right? Let's say the background is brighter. So the background will be, let's say, 182 or something like that, right? So what happens if I average the two together and replace it by the average? It will, see, the average of 25 plus 182 will be close to 100, right? So it's no longer darker, it's becoming now less dark. So you'll see essentially from dark, so these edges will become a little bit smoother. There will not be a sudden transition, there will be a gradual transition. Okay.
When do you do the replacement? Do you have to finish passing the image first and then replace? Because if you're, let's say the first 9 pixels you replace, then that
average you don't replace,
until you're done passing through the whole image.
You keep storing it in a different output, otherwise the average itself will keep accumulating. Okay. Anyway, so what we looked at first kernel was our simple low-pass kernel. Okay, so let me represent this by L, low-pass kernel. And once again, the typical terminology is we use lowercase letters for the time domain or the pixel domain, and we use uppercase letter for the frequency domain. Okay, so L over here is the low-pass kernel, and as we discussed for a 3 by 3 kernel, what will it look like? 1 divided by 9. Okay, so just like we have an impulse in the time domain, and as we discussed, if we do the convolution of delta of t with any signal, we get the original signal. So the question is, in the pixel domain, what is the equivalent of the delta t? It is, so what do I do a convolution so that the original image stays unchanged?
1 in the middle.
1 in the middle, exactly. Okay, so let's call this I, short for identity, or just like we have the identity matrix, but I in the pixel domain will be this particular kernel, right? Okay. Last time we also looked at another type of low-pass filter, okay, which was the Gaussian filter. Okay, so if you take a look at the Gaussian expression, okay, g of x, y, in so this is, because pixels are two-dimensional data, right? So in the 2D we discussed this is 1 over 2 pi sigma square x squared plus y squared. Right, so this was our expression. So then what is the exact kernel? What numbers do we put over here? So I showed you a technique how you'll come up with this. You will create a grid. Okay, x is 0, y is 0, x is 1, y is 0, right? X is 1, x is 1, x is negative 1, negative 1, negative 1. Okay. Here y is 1, y is negative 1. Okay. X is 0, and x is 0. Here x is negative 1. Sorry, y is 1. And y is 0.
Negative 1.
And y is negative. And here y is negative.
And 1 on the
And 1 on the top. So we feed in x of 1. So for example, if you wanted to do over here, you'll set x equal to 1, y equal to negative 1 in this equation. You'll pick some value of sigma. Let's say sigma equal to 1.2 as an example, or 1, or whatever value you wanted to pick. So whatever number you get will be the value of the kernel over there, right? Now, one of the rules was when we add up all the kernel values, they should sum up to 1. So then, as we discussed, what you will do is you'll add up all the numbers and then divide each value by that number so that the sum comes out to be 1. Okay. Sometimes what we further do is convert it into, let me see if I can quickly show you. Anyway, if you Google Gaussian kernel, one of the links will be, giving you the actual equation. What does the Gaussian kernel look like in 2 dimensions, right? This is what the shape is. Okay, so once again, you'll pick some sigma on that grid, 3 by 3 grid. You can compute the values and come up with the kernel, right? So I showed you one way in the last lecture of what if you wanted a 5 by 5 kernel? So 5 by 5 Gaussian kernel. So then how would you compute it, right? So you will come up with a 5 by 5 grid first of all. Okay, center will be x of 0, y of 0, right? Then x of 1, y of 0, x of 2, y of 0, right? And same way you start putting in all the, what will be the coordinate of this one?
This one would be
X of 2,
y of 2.
right? So as you can see, this is what they did, -2 to 2. Actually, yeah, they have a little bit more in the, but the actual kernel will be between -2 and 2 in this case, right? Once we come up with the numbers based on a given sigma, again, we'll scale it so that we add up all the numbers, divide each number by the sum, so that the total comes out to be 1. So if we did that, then each one of these will come out to be something like this. In the kernel, 0.017, something like this, right? Okay, so we could leave it like this as long as the sum is equal to 1. Or sometimes what we do is we divide it by the smallest number so that we can make it an integer. Okay, so whatever is the smallest number, if I divided it by, then suppose the smallest number is 0.033. Let me pretend, then what will happen to this one?
0.0.
Sorry, 0.0033. Like third of it. Then this will change to 3, right? Okay, so anyway, if we did that, so here's an example of the kernel. So if we divide by the smallest number, so the smallest number obviously will appear over here, so that will be 1, correct? So all of these will become integers, and we'll round them to the nearest integer, right? And then because the sums still have to be equal to 1, then where's this number coming from?
Total.
It's the total. So we add up, divide by this, right? So typically when we program, because integer division is, integer multiplication in a computer is faster than a floating point multiplication. So typically we use the integer technique and do one division at the end. Okay. Take a look over here. Where's the maximum value appearing in the kernel?
Middle.
In the middle, right? And then gradually it tapers down on each side. So essentially this is reflecting this shape over here. Okay. So this is one type of kernel. And what kind of frequency behavior Gaussian kernel gives us? High pass filter, low pass filter, band pass filter. So anybody remembers?
So the same thing was frequency domain.
It's just
See,
a high
if
one.
this is in the pixel domain, right?
Low pass.
Pretend this is a 2D picture. Once we do the Fourier transform and take a look at the frequency domain, it looks the same. Okay. So essentially, it is blocking certain frequencies after a certain point, right? So this is once again one kind of low pass filter. Okay. By controlling the sigma, as we discussed in the last lecture, we can make it sharper, meaning after a certain frequency, block everything, or make it very gradual. Okay. What will happen if we created sigma very high?
So it will have a lot of frequencies.
Huge.
Won't it look like something like
Yeah.
this? How will it compare to this filter?
More or less the same thing.
More or less the same thing. Okay. So, actually, sorry, my mistake. If we make it very, very wide, it's not doing anything. It's not appearing like this. It's appearing more like other way around. Let me think. In the frequency domain, if it is very wide,
Identity matrix.
then it's passing all the frequencies. That means it's not doing anything to the.
So identity matrix.
So it will be more like an identity in the pixel domain, because this is the frequency domain behavior. No. Okay. Yeah, sorry. It will behave more like this, because see, the inverse transform of this will still be like this in the time domain. And then so it will behave more like this. It's doing like multiplying everything by 1 and then averaging. Okay, either way. So Gaussian filter is one way to accomplish low-pass filters. Okay. So Gaussian kernel. One kind of low-pass filter. Okay. The nice thing about the Gaussian is, like I said, by controlling the sigma, we can control, what kind of frequency behavior will come out of this particular filter, right? Very briefly, I'll show you there's another binomial type of filter, okay, which is based on Pascal's triangle. Okay, Pascal's triangle looks like this. Okay. Then if I go one more row,
1, 3, 3, 1.
so then we'll put 1 over here,
2, 3.
and 1 and 2 is 3, 2 and 1 is 3. So basically this is how it does. Okay. If I go one more row as an example, so what will happen? You add 1 and 3,
6,
4.
1, 4, 6, 4, 9, 10.
So for example, if you wanted to create a 3 by 3 kernel, okay, what you will do is You'll start out by, for example, 1, 2, 1. Okay, now the second number over here is 2, right? So what you'll do is you'll multiply it by 2. So this will become, 2, 4, 2. And then 1 to 1, you just repeat it. So this will be a 3 by 3 binomial kernel. Okay, what if we wanted to create, we have to divide it by, so what's the sum of all of these? 4 for 8 and 8, 16, so divide by 16 will be the binomial kernel, right? What if we wanted to create a 5 by 5 kernel? A 5 by 5 kernel will look like this: 1, 4, 6, 4, 1. Okay, then we multiply this by 4. So 4, 16, 24. Then we multiply the same row by 6. 6, 24, 36, 24, 6, and then 4, 1, 6. Then we just basically mirror it. So 16, 4, 24, 6, 16, 4, and 4, 1. So my question to you guys is, by looking at it, what kind of filter is it?
Gaussian.
No, I mean, in the same.
I mean, even though the values are different from Gaussian, but doesn't it
Same
looks
pattern.
like a Gaussian?
Yeah.
So it also will produce a low pass filter. Okay. Now, just as a very small side interest, these binomial coefficients appear in many real life systems. For example, if you were doing, let's say, x plus y squared. Okay, remember this would be x squared plus 2xy plus y squared. If you take a look at the coefficients of each term, what will they be? 1 to 1, right? Same way if you do x plus y cubed. This will be x squared plus 2xy plus y squared. Multiply it further with x plus y. So this will become x cubed plus 2x cubed y plus xy squared. Then if I go y, x squared, x cubed y plus y, 2x squared, so 2xy squared plus y cubed. And if I add them, what will this become? X cubed plus 3x squared.
So that should be x square.
All 3x squared?
X square y.
This is x squared.
Yeah.
X squared plus 3xy squared plus y cubed. So if you take a look at the coefficients of these, what are these?
1, 3,
1, 3, 3, 1. So this is, so same way if you did the raised power 4, you'll get that expression, right? So anyway, that's where the pattern comes from. Okay. So sometimes we use the binomial coefficients to create filters. If you can just remember for the time being, because most of the time we'll use 3 by 3 filters for computational speed up. So for a 3 by 3 filter, the binomial coefficients are 1 to 1. Okay. Anyway, so now let's take a look at slightly more interesting filters.
Is that 3 by 3 the minimum size for a filter?
3 by 3 is the minimum size for a filter. We always go in odd sizes so that we have a center pixel on which we can see the surroundings. So 3, 5, 7, and so on. Okay, so now let's take a look at high pass filter. Because so far we've looked at low pass filters, which remove which remove high frequencies and pass the low frequencies. So high pass filters are used to do the reverse,
So set a high point.
meaning,
No.
okay, meaning we want to sharpen the picture. Okay, so if you took a picture from a distance, right? Then like I said, if there's a picture of a tree, it might look blurry. This may look diffused with the background. So if we wanted to make it, very, very sharp, we'll pass it through a high pass filter and block the low frequencies. Okay. So our goal, as you can see in the frequency domain, will be to create something like this. Okay, so this is frequency, this is HFF, meaning block the low frequencies after a certain frequency, you pass them as is. Okay. So one way to accomplish this, see, so far we've only learned low pass filters, right? So how do we create a kernel for a high pass filter? Easy way would be, think of it this way. Think of this as all pass minus low pass. Right? If I subtract this, okay, let me make it approximately same width. So this is all pass minus
Low pass.
low pass.
So identity matrix minus.
Okay, what is the kernel for the all pass?
Identity matrix.
Identity. So this is, we already know. This will be 0, 0, 0, 0, 1, 0, 0, 0, 0, right? Minus low pass,
All one has been like
I mean, this would be a simplest high pass filter. Okay, so if we did that, you can see what will this come out to be? -1, -1, -1, -1, -1, -1. Sorry.
0.
See, this is 1/9. 1 minus 1/9 will be 8/9. Divided by 10.
So it's 0, some.
Sum is 0 anyway, so whether we divide by 9 or not doesn't matter, but to be theoretically correct, we'll just leave the 9 over there.
So can we derive to a conclusion that if you want to design a high pass, the sum should be 0 of the determinant matrix? Is that the conclusion?
No, it doesn't have to be 0, because in this example it came out to be 0, but in other examples, what if I pick this to be a Gaussian?
Oh,
Then it would be different. Okay. So anyway, so this would be the kernel for a simple high-pass filter, right? So what if I gave you a 3 by, so let's create a high-pass filter. Based on low-pass binomial filter. What will be the kernel for that? So the kernel for that will be
1, 2, 1.
minus 1, 2, 1,
2, 4, 2.
2, 4, 2,
So that means
divided by 60, right? So what will that come out to be?
0 minus 1, minus 2.
Minus
minus 1, minus 2, minus 1.
minus 1.
Minus 2.
Let me leave this all minus 1.
Oh.
Okay, so this one will be 1 minus 4/16, which is 12/16, correct?